Okay, so start with your talk about multivariate correlation attacks and not only.
Okay, well, thank you very much for organizing this conference, and thank you for accepting my paper. And today I'm going to talk about the multivariate correlation attacks on cryptanalysis and the cryptanalysis of LFSR-based stream ciphers. I'm a PhD student at the University of Bergen, and this is joint work with my supervisor, Igor Semayev. Well, first of all, thank you, Enrico, for introducing the filter generator, so I can go quickly on this slide. Practically, we have the LFSR here at the top, and the LFSR is defined by the degree and feedback polynomial G over F2. We're working on a binary field here. The content of the register at a given time I, we call it the LFSR state at time I, and usually we just see this as a vector, in this case over F2. And all the bits that are produced by the LFSR, we call them the LFSR sequence. The other block that is used in a filter generator is the filtering function f, which is a Boolean function, in this case in L variables, and the inputs are taken by some of the contents of the register. And the output of the function at the given time I is the keystream bit, and the collection of all the keystream bits is called the keystream. One of the most powerful attacks against any crypto system in general is the key recovery attack. And in the context of the filter generator, it means to recover the LFSR initial state if we are available or if we have n keystream bits available. In this case, the initial state is nothing but the state of the LFSR at time I equal to 1. The attacker has access to the feedback polynomial G, the filtering function f, and the indices that are taken as inputs to the Boolean function f. And there are many different types of key recovery attacks against the filter generator. Among them are the algebraic attacks that Enrico explained in the previous session. Another type of attacks are fast correlation attacks, and those are the ones that are relevant in the context of our work. We have also deterministic attacks and some other attacks, particularly the time memory data trade-off, are well known as well. Fast correlation attacks were first introduced by Meier and Staffelbach. And it was actually an improvement of the correlation attack by Siegenthaler. If you are interested in knowing more about them and maybe read a lot about the many different improvements and developments, the survey by Agren et al. Is a really good piece of bibliography. The basic idea of the fast correlation attack is to exploit the correlation between the LFSR sequence and the keystream. Particularly, we are interested in computing the probability P, which is called the correlation probability, that the keystream bit at time I is equal to the LFSR bit at time I. This problem can be seen as a decoding problem. And this type of attacks usually use parity checks with low weight D. I'm gonna go into the details of a parity check in the next slide. And the complexity, the time complexity depends mainly on the correlation probability P, the available number of keystream bits N that we have, and the weight of the parity checks. A parity check is a polynomial that is a multiple of the feedback polynomial G, we call the number of non-zero terms of the parity check its weight or density, and if the number D of non-zero coefficients of this parity check is small, we call it a low density or low weight parity check. The number of available parity checks that we can obtain given the length n keystream depends on n per se and on G, the feedback polynomial. And for correlation attacks, it is important to get as many parity checks as possible, because the more parity checks we have, the lower the complexity is. Okay, so those were the preliminaries. So now I'm going to present the model for our new attack. And I just need to introduce a bit more of notation. So if we denote by M the companion matrix of G, that is nothing but the square matrix that somehow encodes the clocking of the LFSR. And then we denote by capital Greek letter lambda, the matrix that somehow selects the input to F. We can write the input to the Boolean function at time I, which is this vector, at the matrix vector multiplication that is written here. Particularly with the companion matrix, we can express any state of the LFSR in terms of the initial state in this way, and then we just multiply here the selection matrix on the left to get the input to the Boolean function. Then we define a matrix AI by the multiplication of these two matrices, and then we can write the keystream bit at time I as it is written here. It's the filtering function, and the input is the vector at time I. With this, we can re-express or restate the key recovery attack the following. We want to find a vector X such that this conditional probability is maximal. And practically the conditional part of this equation is nothing but the available keystream that we have. So now I will introduce the new method that we developed. But first of all, I would like to introduce a more general problem. So if we have n matrices that are denoted A sub index I, and these are matrices over a finite field of Q elements, these matrices have size Li times n, and we also have n, well, capital N, different probability distributions on this vector space. The problem that we want to find, or the problem that we want to solve is to find a vector X such that this statistic here is maximal and the value of this vector has non-zero probability for all probability distributions. So here we are just stating the problem in a more general setting, and then with the modeling that I showed you before, we can easily reduce let's say the equations from the filter generator into this more general framework. Then in order for us to solve this this problem, what we do is we use a maximum likelihood method, and the basic idea is to distinguish whether the values given by this matrix vector multiplication are taken from actually the probability distributions that we're interested in, or the uniform distributions on the corresponding vector spaces. If the value of n or if n is large enough, then we can find a unique solution. Otherwise, we may find multiple solutions. And the complexity of this approach is capital N times q to the n operations. We also developed an improved method for this multivariate correlation attack, which has complexity as it is written here in this equation. And in order for us to achieve this complexity, we employ the fast Fourier transform, and therefore we also need a q to the n, or the space complexity is q to the n. And we can see the improvement that we did here as a multivariate extension of the work by Chose et al. In the binary setting. It's also important to mention that the original correlation attack by Siegenthaler is a particular case of our correlation of our multivariate correlation attack, in which Q is equal to 2, L is equal to 1. So that means that the matrices AI are row vectors, and there are only two different probability distributions. And also another important thing to mention is that with the modeling that I showed before, we have the special case that all the probability distributions PI have the particular characteristic that their support are uniform, they are uniformly distributed on their support. That means that the statistic Sx is always a constant, and in this case, the attack is equivalent to brute forcing the initial state of the filter generator of the register, which is not good. Then we developed what we call relations modulo VR, and I'm going to be a bit general here as well. So VR is a matrix of size R times N of rank R, and then we call a relation modulo VR a subset from the set of natural numbers from 1 to n, such that the vector space generated by the rows of the matrix VR has a non-trivial intersection with the vector space generated by the rows of all the matrices indexed by our subset I. The cardinality of the subset I, denoted by D, is called the weight. And if this number D is small, we call it a short relation. And in simple terms, we can think of these relations modulo VR as a generalization of the parity checks that are used in fast correlation attacks. And each relation modulo VR induces this probability distribution. And particularly, we are happy with this probability distribution because it is non-uniform on its support. Therefore, we can apply the multivariate correlation attack that I presented before. As I mentioned, relations modulo VR are more general than parity checks. And particularly, given a keystream of length n, we are able to find more relations of weight D compared to parity checks of weight D. So that's really important and advantageous for us because we can actually reduce the data complexity for our attack, as I will show later. So having the idea of the multivariate correlation attack and having the idea of the relations modulo VR along with their probability distributions, I can show you how we can mount the attack and actually get the initial state of the register. So our attack comprises two stages. The first one is pre-computation and the second one is the main computation. For the pre-computation, we just generate a matrix B of full rank, and we will denote by B sub index R, the submatrix of B comprising of the first R rows. So what we do is compute a set denoted here by calligraphic I sub index R. So we compute a set of short relations, and we associate each set to each matrix BR and compute the probability distributions. Then using those probability distributions, we compute a threshold C such that we find the correct solution with probability beta. So practically beta is the success probability of the algorithm, and that's a parameter. Then in the main computation, we have two variants. We have a tree search and what we call the hybrid approach. The tree search, as the name implies, uses a tree. And particularly what we do is we want to distinguish, as in the multivariate correlation attack, a vector B, which is given by BR times X, which is actually the solution that we want to find. So we compare the maximum likelihood indicator associated to the vector B and compare it against the threshold that we computed before. So you can imagine us having a branch, and the branch represents one of these candidate solutions B. We compare it, and if the comparison or the maximum likelihood indicator is positive for us, we take that solution and we extend it to the next level and then compare again. And if it passes, compare again, and so on. And whenever we reach the last level, in this case level N, we find a solution for our problem. and executing the whole tree search, we can find all solutions to our problem. The hybrid variant it also uses the tree search, but it doesn't start from level 1. What we do in the hybrid variant is we computed the statistic S for all possible candidates at that given level. Having computed the statistic, we rank the vectors B according to the value of the statistic, and then we apply the tree search in that order, starting from that level. So the idea is that at level R0, the correct solution or the correct solutions are ranked or have a very high rank, and then the tree search find them really quickly. Now it is important for us to estimate the number of nodes that we will be visiting at each level of the tree search, because that is what will dictate the complexity of our algorithm. So at each level R of the tree, the number of survivors, meaning nodes that we visit, is given by this expression here, where alpha subindex R depends on the maximum likelihood indicator. And we use a multivariate normal approximation to compute this value. And the complexity, as I was mentioning before, depends directly on that value. So here I have a really short example of the tree search. So we start here. We check. Let's go here first to number 1. So we check here against the maximum likelihood indicator. In this case, this doesn't pass the test. So we cut the branching here and we don't continue. So we go instead to 0, check here, continue here. Here I don't pass the test, then backtrack and carry on. And we follow in the same way up until we reach the last level. And in this case, 0010011 is the solution to the problem. Now I will present some of our experimental results. For instance, we have the filter generator defined by this feedback polynomial, filtering function, and spacing. And we were able to get the initial state using only 5,000 keystream bits. Here I am showing the complexity for both the tree search and the hybrid variant. And particularly for the tree search, I am also showing the complexity of the, let's say, theoretical complexity that we got by using the multivariate normal approximation and the experimental one. It is important to mention here that these indices K span the whole register. So it means that one of the entries is at the first and another entry is the last cell of the register. And that is important because then a brute force attack on this device is equivalent to the 40. And here we can clearly see that our method is much more efficient compared to the brute force approach. And here I show a plot with the number of survivors that we get at each level. The dots represent the tree search only approach. The non-filled squares represented the theoretical, which is the multivariate normal approximation that we have. And with this, we confirm that our theoretical analysis is adequate because the experimental data follows the theoretical curve quite well. And here the circles represent the number of survivors that we get from the hybrid approach. In this case, we computed the statistic for all possible candidate solutions at level 20, and from there we executed the tree search. And our expectation was correct, as in the number of survivors is reduced greatly because the correct initial state was actually ranked very high after computing the statistic. I'm gonna quickly show you another experiment for a rather larger LFSR. In this case, the LFSR has length 64, and our experimental results show that our method is way faster than brute force. And here I show a similar plot to the compared to the previous experiment. The only difference here is that we were not able to execute the full experiment because the complexity, as you can see, is quite high. To actually execute experimentally to the 50 is quite difficult to simulate. And here I'm showing a table in which we compare some of our experiments with other fast correlation attacks, and particularly I just want to point out that for similar parameters, we usually use less keystream bits compared to all the other works that I am citing here. And I would like to conclude this talk saying that we also applied our method to some grain ciphers. And the main takeaway is that we are able to recover the initial state of the LFSR part only of the grain ciphers, because grain incorporates an LFSR and NFSR. And compared to one of the best attacks against the grain family of cipher, which is the work by Tudo et al. In Crypto 2018, we are able to get the initial state using less keystream bits. However, our complexity is higher. And we also were able to do a similar analysis of a grain version 1. But for that, we were able only to compute linear approximations with higher correlation compared to the ones that were reported by Todo et al. In the same paper. We still need to compute the theoretical complexity for the full attack against grain version 1. And that's all from my side. I don't know if you have any questions or if there is time for questions.
Okay.